Every single millisecond, that little router in your home is making a decision that literally keeps the internet working. It's not magic, not at all. It's actually a really simple, kind of elegant piece of logic, and today we're going to break down the one core question a router has to answer so you can see exactly how it thinks.
So here's the big question, right? A packet of data shows up. It's got a destination, but the router is sitting at a crossroads with, a bunch of potential paths. How does it instantly know which one is the right one? That's the mystery we're going to solve together.
All right, so let's dive into our first section, a router's big question. And seriously, if you want to understand how the entire internet functions, all you really need to get is this one simple question a router asks itself over and over again. It's the key to, well, everything.
Okay, so that packet arrives, and the router becomes laser-focused. It ignores everything else, the data inside, who sent it, all of that. It only cares about one critical piece of information, the destination IP address. That's step one, and right now, it's the only thing that matters.
So we can follow along on this little journey. Let's use a real example. Our packet is trying to get to the IP address 192.168.10.34. Go ahead and burn that address into your brain because we're going to be seeing it a few more times.
Okay, moving on to section 2, networks, not hosts. Now listen up, because this next idea is probably the most important mental shift you need to make. If you get this one concept, I promise you'll understand the fundamental logic of every single router on the planet.
And here it is. This is the whole shebang. Routers only care about networks. They don't care about your specific laptop or your phone or any individual device. They're built to think in terms of entire neighborhoods or, well, networks. They send traffic to a whole network, not to a single house on the street.
And this really breaks it down perfectly. On the left, you see how a router thinks. It sees the entire neighborhood, that whole cloud of devices. And on the right, that's what it's designed to ignore, the specific laptop or phone inside that neighborhood. For the router, it's all about the group, not the individual.
All right, section 3, reading the router's map. So if a router only cares about these networks, how in the world does it know where they are? Well, it uses a map. And in the networking world, we call that map a routing table. It's basically the router's personal GPS for the entire internet.
And when you boil it down, a routing table is super simple. It's just a list. Think of it like this. On the left, you've got the destination networks it knows about. On the right, you've got the directions. To get to this network, send the packet that way. That's literally it, just a set of directions to different digital neighborhoods.
So where do these entries on the map even come from? Well, they're created through something called subnetting. When a network admin carves up a big network into smaller, more manageable subnets, they are literally drawing the destinations on the router's map. The two things are inseparable, you just can't have one without the other.
Okay, section 4, finding the perfect match. So let's recap. The router has the destination IP from our packet, and it has its map, the routing table. Now the search begins.
So what the router does now is run a series of simple tests. It takes our destination IP, remember 192.168.10.34, and it compares it against every single entry in its routing table, asking just one question over and over. Does this address belong inside the range of this network? First up, it checks against the 192.168.10.0/27 network. Now that /27 tells the router how big the network is. A quick bit of math shows this network only includes addresses up to .31. Our destination is .34, so nope, that's a miss, no match. The router just moves on to the next entry on its list.
Next, it checks our IP against the 192.168.10.32/27 network. This one covers all the usable addresses from .33 all the way up to .62. And our destination, .34, fits perfectly inside that range. Bingo, we have a match. The router now knows exactly which path to send the packet down.
But hang on a second. What happens if the packet's destination could actually fit into multiple entries in the table? This is where the real genius of routing logic kicks in, and it all comes down to one simple, elegant, golden rule. So, check out this scenario. Our CMIP address 192.168.10.34 actually matches 3 potential routes. It fits inside a big, broad /24 network, it fits inside our more specific /27 network, and, of course, it technically fits inside the default just send it anywhere route. So which path does the router choose? It has to make a decision.
Well, the tie is broken by the golden rule of routing. It's called the longest prefix match. It's a really simple but powerful idea. The router will always prefer the most specific, the most detailed route it knows about. It's kind of like choosing a specific street address over just a zip code, yeah? Both are technically correct, but one is way more specific, right?
And here's how it makes that call. The router simply looks at the prefix length. A /27 is longer than a /24, which makes it a more specific, more detailed entry on the map. And the router always trusts the most specific information it has. So the /27 route wins every single time, and the packet is sent on its way.
So we've gone pretty deep into the logic here, but let's zoom out for a second. Why does this whole system of networks and longest prefix matching, why does it matter so much? Why is it the foundation of the entire internet?
Well, the answer really comes down to two words: efficiency and scale. I mean, think about it. If routers had to know about every single device, their maps would have billions of individual addresses. It would be a chaotic, unmanageable mess. But instead, by dealing with these nice, organized networks, routing tables stay small and efficient. Without this logic, the internet as we know it, it just couldn't exist.
Okay, so let's do a quick recap of the key takeaways here. First, and most importantly, routers see the world in networks, not individual devices. Second, subnetting is the process that actually draws that map the router uses. And third, when there's more than one right answer, the router always follows the golden rule. The longest, most specific match always wins.
Which leaves us with one final thought, doesn't it? The router's logic for choosing a path is, for all intents and purposes, flawless and totally predictable. So, when things go wrong on the internet, it's often not because the router made a bad choice from its map, but because the map itself was drawn incorrectly in the first place. And that opens up a whole new can of worms for next time.